lecture number 9. And we start our chapter of superconductivity. So, the plan is as follows. So today we discuss several things. In particular, we discuss experimental evidence of and discovery of superconductivity. Then we discuss Meissner effect with very simple derivation of London equations, and then I recapitulate for you the Hamiltonian of electron-phonon interaction, and we will see that under certain conditions, electron-phonon interaction leads to attraction of two electrons being in the vicinity of the Fermi surface, and then we discuss Cooper instability. This is the plan for today, so I'm afraid I will need 5 or even 7, 8 more minutes. On Friday we discussed Ginzburg-Landau theory, so whole lecture will be devoted to Ginzburg-Landau theory, and I will do some details of derivations because I'm afraid not all of you are very familiar with functional derivatives, so with variational methods when you take a derivation with respect to little change of the function. And this is important. Then on the lecture, on Monday lecture, we discussed microscopic theory of superconductivity, which is part in Cooper-Schrieffer theory. And again, I will rely upon the Boголюбов transformation, which we introduced for bosons when we discussed the Bose-gas. And the last lecture will be devoted on superconductivity, which means Wednesday next week will be devoted to properties of superconductors, namely thermodynamics of superconductors, electrodynamics of superconductors, and if time permits, we discuss Josephson effect. This is overall plan for superconductivity, and then in the very last chapter we proceed to magnetism, and again there will be 3 very condensed lectures on magnetism, and then on the lecture number 16, namely the last lecture, I will make an overview of these 2 chapters, superconductivity and magnetism, and we discuss new development in the theory of high temperature superconductors and strongly correlated systems where magnetic instabilities compete with superconducting instabilities. This is the plan. Okay, so but today we begin with superconducting. And first of all, in 1911, the Dutch physicist Camerlin Onnes realized that there are certain metals, in particular mercury, which behaves in very unusual way when you cool this metal down. So you know that mercury is metal. What happened is that the resistivity of these metals is dropped at certain temperature, so this is resistivity. And of course it grows when temperature goes up. What is unusual, because below the critical temperature, this metal conduct electric current without any energy losses. This was first observation, and then the second observation was that not all metals behave like that. For example, there are some metals which do not become superconducting even for very low available temperature. For example, copper resistivity reaches its value where it's saturated at 0 temperature. Again, as I said, it's lowest possible available temperature, and still for now the experiment where the lowest possible temperatures of the order of millikelvin, I mean for bulk condensed matter experiments. For ultra-cold gases, we discussed that the temperatures are much lower. Still, some metals do not superconduct. So then the question was, what is the mechanism? What is the phenomenon? What is the mechanism behind? And why different metallic systems behave differently? So mercury, as I said, the critical temperature of superconducting transition is of the order of 4 Kelvin. For tungsten, Temperature is much low, but it's still superconducting. It's 0.015 Kelvin. For niobium, it's 925 Kelvin, and so on and so forth. So, what is the mechanism which is leading to very different temperatures? On what property this mechanism depends, and most important, how to engineer the material which will give us the highest possible temperature of superconducting transition. So all these metals superconduct below helium, liquid helium temperature. And as I said, producing liquid helium is a very expensive procedure, and therefore the material science problem, so to say, was formulated how to find such material which could superconduct at least at temperature of liquid nitrogen. So liquid nitrogen, the temperature when nitrogen becomes liquid is 77 Kelvin. So anything with the temperatures of superconducting transition higher than the temperature of liquid nitrogen would be considered as high temperature superconductors in this sense. Because producing liquid nitrogen from the air is not that expensive as producing liquid helium. And I should say that for more than 70 years, the biggest success of in material science to engineer materials with highest possible temperatures of superconducting transition was in niobium-3 germanium alloys, where the critical temperature was about 24 Kelvin. So you see, it was not that fantastic progress during 70 years of research. And in 1985, the breakthrough occurred when two scientists in Switzerland, in Bednorz and Müller, synthesized lanthanum-based copper oxide when the critical temperature was about 40 Kelvin. So you may say that this is not much. However, it was really breakthrough, because the very same year another system of yttrium copper oxide was synthesized where the critical temperature was about 90 degrees. So this is the same family. This system possesses many similarities in their properties. So it contains copper and it contains oxygen, and we discuss properties of high temperature superconductors. So this is beginning of the age of high temperature superconductivity, and I will revise you and review you the model success in copper oxide-based system and iron selenide-based system, yet another new system of high temperature superconductivity, and the very last lecture. So now the goal is to find a superconductor which will superconduct at room temperature. This goal is not yet achieved. To my best knowledge, the highest possible temperature of superconducting transition is an thallium-based copper oxide, which is of the order 170 Kelvin. So it's much higher than temperature of nitrogen, but still, you see, this is challenging problem. Besides, while we discuss the mechanism of superconductivity superconductivity, which explains well the properties of conventional superconductors. I would call this conventional superconductors, and their mechanism is well understood. The properties of high temperature superconductors, namely the mechanism behind of this unusual behavior, is not understood, and this is also one of the challenging problems of modern condensed matter physics. Let me continue with properties of superconductors, which were experimentally discovered, which allow me to draw some conclusions and build some elements necessary to construct the theory. So first of all, it appeared that the specific heat of the superconductor has jumped at the critical temperature. The jump in specific heat, which is second derivative of the free energy, means that the superconducting transition is the second order phase transition. So we do have some continuous second order phase transition. Then the superconducting metal and normal metal were put in contact and connected to the electric circuit, and the IV curve for the superconducting transition, the IV curve was measured at low temperatures. So this is current, and this is applied voltage, and we know that normal metal behaves in accordance with Ohm's law, namely the current is proportional to the voltage, where the coefficient is the conductivity, which is inverse to resistivity quantity. However, in superconductors, the IV curve is highly nonlinear at low voltages. Moreover, there is no current below certain critical voltage. All these properties are consistent with the statement that there is a gap in the spectrum of elementary excitations. So the elementary excitation should be charged. We know that in normal metal, which is normal Fermi liquid, the excitations are gapless. These are electrons and holes. You just remove state from the inner part confined by the Fermi surface and put it outside, so you create electrons and hole excitations. Here, the excitations in superconductors are gapless, are gapful. Therefore, we may say that the gap itself is order parameter, and it continuously goes to zero. So the low temperature state is characterized by spectrum of gapful excitations, while at high temperature, where superconductivity is destroyed, we have gapless excitations as in normal metals. So let me say 1, 2. Then it was discovered that if you put superconductor in magnetic field, so suppose you have normal metal, you put it in magnetic field, and of course magnetic field penetrates freely into the normal metal. However, if you put the superconductor, it was discovered that magnetic field does not penetrate into the superconductor. In this sense, superconductors are ideal diamagnets because you apply magnetic field and the magnetization of this system is such that there is something feedback which is formed inside superconductor, which compensates the external magnetic field such a way that magnetic field is zero, So this is a diamagnetic response. So this is a Meissner effect. Moreover, superconductivity is destroyed not only by the temperature, but also by magnetic field. So at sufficiently large magnetic field, the superconductivity is destroyed. Okay, so, and since superconductivity looks very similar to phenomenon of superfluidity, because as you see the current proliferate through the metal without any energy losses, then it was immediate conclusion that the superconductivity is superfluidity of something. We will discuss what this something is, and therefore this two-fluid theory, which we discussed for the superfluidity, namely that below transition to the superfluid state, there is a two-component liquid, and one component is just a normal component, and another one is superfluid, can be equally applicable for explanation of the properties of superconductors. So what I will do now in a few lines, I will proceed with very simple calculations, derive equation for the superfluid current combined with Maxwell equations, and explain the Meissner effect, why there is no magnetic field inside the superconductor. This is the goal for next 10 minutes. Any questions so far? And of course, superconductivity is related to superfluidity of some charged quasi-particles. Because these charged quasi-particles conduct charge current. We say in the theory of superfluidity that there is a current H over 2m. I'm interested in the charge current, and let me say that the carrier, which I don't yet know, is characterized by some effective charge. This is why I will put E star and some effective mass, since I don't know yet what is conducting charge. And I have I psi gradient psi dagger minus psi dagger gradient psi. And we discussed for superfluidity that we can characterize our superfluid below the Bose-Einstein condensation transition by the global wave function. So the wave function is then square root over ns e to the power I chi, and then we plugged in this psi. I'm saying that if I proceed the very similar way, the only difference that I multiply everything by charge, because I'm considering the charge current, then I will get that superfluid current is associated with the gradient of the phase of the global wave function. So this is H over m star E star ns, and gradient chi. This is what we said, and therefore I associated superfluid velocity with the gradient of the phase. So this is H star over m star gradient chi, and therefore this is E star ns ds. So this is what we would have if we translate one-to-one our knowledge about superfluidity to our knowledge of superconductors. But we need to make one new step. We are going to consider superconductors in the magnetic field. Therefore, I need to add magnetic field to the equation for the superconducting current. And we know how to do it. In a magnetic field, our operator, our momentum, which is minus I nabla, should be replaced by minus I nabla minus E star over HC vector potential A. This is what happens, and we know that nabla times A is the magnetic field. I will also write here on the right hand side some Maxwell equations which I need for further derivation. In particular, I will need equation that nabla times B is associated with the current. So this is 4 pi over C GS. And yet another equation which tells us that there is no magnetic charges, there are no magnetic charges, which is divergence of B is equal to 0. So these are two Maxwell equations. And this is connection between magnetic field and the vector potential. So what I need to do here, let me multiply this by I minus I, IH E star over 2 M star, I times minus I is 1, and I repeat the very same, chi nabla chi star minus psi star nabla chi, nabla psi, sorry, which is I and I is equal to minus 1, so I will invert the order of these terms, so I will write it down as H bar E star over 2M, and I have psi star minus I nabla, psi minus psi minus I nabla psi star. Yeah. So these are complex conjugated terms. So this one, for example, is plus psi minus I nabla psi complex conjugated. Therefore, I can now elongate my derivative, and what I will get factor of 2 because of the phase appearing in the two terms, which will cancel out factor of 2, and I have twice E star over HCA times psi modulus square. Psi modulus square gives me NS, so psi modulus square is equal to NS. Psi modulus square will come out when I don't differentiate the modules. So I assume that the modulus of superconductor density is uniform. Therefore, what I will obtain, this is H E over M star NS, and here I have gradient chi minus E star over HC. So you see by comparing these equations that in magnetic field you have extra term associated with vector potential. So if now I apply the nabla operator to my superconducting current, so namely nabla times J S, then it's equal to nabla applied to the gradient of chi and nabla applied to A. So I have H E star over M star and S, and here I have nabla times nabla chi minus E star over HC, but nabla times A is B, so I will write it like this. And of course, as we discussed it, for any function, nabla times nabla times chi is equal to 0. So circulation of the gradient is equal to 0. So this term doesn't exist. Based on this property, we discussed the behavior of superfluids and discovered that there are some vortices. So what I have at the end of the day, that nabla times Gs is equal to minus h bar E star square over m star n s h c, so h bar cancels out, and b. So let me take this equation and this equation, assuming that divergence of B is equal to 0. So, and moreover, let me apply then nabla operator to the left and right hand side part of this Maxwell equation. So nabla times B is equal to 4 pi over C nabla times Gs, and this in terms is equal to minus 4 pi over C E star square over m star C times B. So in next 2-3 minutes I will work with this equation, and since if I apply twice differentiation over vector B with respect to the direction, this term and this coefficient should have dimension of size or dimension of the length square, and therefore I will call this coefficient 1 over lambda square. So this is 4 pi E star square divided by m star C square. So it has dimension of length, and I will call it lambda. So the equation what we got so far is nabla times B is equal to minus B over lambda squared. So this is differentiation operator. I will show you the way to compute the left hand side, but I assume that you also know how to do it in a very efficient way. So let me first consider the component alpha of the left hand side. So since it's a rotor, this is epsilon alpha beta gamma d over dx beta, the gamma component of this operator. So this is epsilon gamma mu nu d over d mu b mu. Okay? Do you understand what I have written down? So this is Levi-Civita tensor epsilon alpha beta gamma, where alpha beta gamma takes value x, y, z, or 1, 2, 3. The same is here. Gamma mu is a fully antisymmetric Levi-Civita tensor, which possesses properties that this tensor is equal to 0 if any two of these indexes coincide, and the permutation 1, 2, 3 and any cyclic permutation leads to sign 1, and any anticyclic permutation leads to sign -1. This is a property of Levi-Civita tensor. But what is also known that if you, so for example, what I'm saying that epsilon alpha beta gamma is equal to epsilon gamma alpha beta. I can cyclically permute indexes. And moreover, epsilon gamma alpha beta since I have two indexes which coincide, and I adopt Einstein notations which tell me that any pair of repeating indexes assumes summation over these indexes. In principle, I should write down that the sum over alpha, beta, gamma, mu, nu, and all these things, I assume it without putting sign. So, if now I have a convolution of two Levi-Civita tensors, this is what I have here. This is a determinant of Chronicle symbols, alpha, mu, delta, alpha, nu, delta, beta, mu, delta, beta, nu. So this is delta, alpha, mu, delta, beta, nu, minus delta, alpha, nu, times delta, beta, mu. So what I have here is this delta, alpha, mu, delta, beta, nu, minus delta, alpha, nu, delta, beta, mu, and d over dx beta, d over dx mu, b mu. Again, the index alpha is what I'm looking for. So there is no summation over index alpha because it never repeats twice. All remaining indexes, mu and mu is here, beta and beta here, mu and mu here, assumes repetition, therefore summation. So this is then alpha is equal to mu, so this is d over dx beta, d over dx alpha, because mu is equal to alpha, b, mu is equal to beta, b beta, minus d over dx beta, mu is equal to beta, so I have twice, and mu is equal to alpha, b alpha. You understand what I'm doing? Alpha is equal to mu, therefore this is b alpha. Beta is equal to mu, therefore this is d2 over dx beta squared. If I permute these two derivatives, and I always can do it, what I have with this term is d over dx alpha, d over dx beta, b beta. I just permute. But I have divergence beta equal to 0, which means divergence beta, which is d over dx beta, b beta, is equal to 0. Therefore, this term is 0. So what I have at the end of the day is minus Laplacian b alpha. Okay? Therefore, I have much simpler equation, namely, I will multiply the right hand side and left hand side by minus 1, so Laplacian b is equal to b over lambda squared. Are you with me? So now, let me consider the situation when you have a superconductors here. Suppose this is a plane. This is a z direction. And you have magnetic field, which can be written down as magnetic field parallel to the plane, E parallel, plus magnetic field perpendicular to the boundary times Ez. And since I have geometry of the half plane, the magnetic field can depend only on Z. Right? I'm interested in the question how much of magnetic field penetrates into the superconductor. So magnetic field depends only on Z and can be split into tangential part and normal part. And let me first write down the equation for the normal part. First of all, divergence of B means that d over dz, these are perpendicular directions, bz, is equal to 0. Therefore, I conclude that bz is a constant. If I differentiate this equation with respect to z again, I will get d2 over dz squared bz is of course equal to 0. But from this equation, this should be equal to bz over lambda squared. So the constant bz is therefore equal to 0. Right? So this constant is identically equal to 0. So the conclusion number 1, the normal component of magnetic field doesn't penetrate at all to the superconductor. Let's now consider equation for tangential component. Which is d2 over dz squared b parallel over z is equal to b parallel divided by lambda squared. This is this equation. Divergence doesn't matter anymore because I used it for the component z. So this equation can be easily solved. The solution of this equation, b parallel as a function of z, is equal to b parallel of the boundary times e to the power minus z over lambda. So which means you have some magnetic field. You are saying that you present this magnetic field as Bz and B parallel. The Z component doesn't penetrate at all, but parallel component exponentially decays inside the superconductor. So therefore, the length where Z is of the order of this length, where exponent, the argument of exponent is of the order of 1, is called penetration depth. So what we have seen, that normal component doesn't enter superconductor at all. The tangential component exponentially decays, so there is no magnetic field inside of superconductor. So on the lenses which is larger, which lambda, the magnetic field inside superconductor is exponentially small. Okay. So the conclusion is, I did this exercise in order to show you that I start with some conjecture. I start with some conjecture that the superconductivity is superfluidity of something. This something has effective charge E star and effective mass M star. And based on very simple equations derived for superfluidity, I see that it is sufficient to explain the Meissner effect. Therefore, my initial assumption is correct. I didn't come to any contradiction. Of course, I'm not about to explain specific heat. I'm not about to explain the normal superconductor junction, but what I see that indeed some phenomenology based on the knowledge of superfluidity works very well to explain the Meissner effect. Good. So in order to explain other things, we need to, we can proceed twofold. On one hand, we can build up the microscopic theory of superconductivity based on certain mechanism. We discuss this mechanism next week. On the other hand, we can proceed with the same sort of phenomenology, assuming that the order parameter, so to say, is a wave function, which we did for the superfluid, and build up certain theory, phenomenological theory. This is what we do on Friday. However, the remaining part of today's lecture will be devoted to building up key elements for Monday lecture. So, this is what is done, will be very important for Friday, but from now on, I would like to discuss some arguments behind the mechanism of superconductivity. Any questions? Okay. There was yet another experimental observation which was very important, namely, if one takes the super metal, which becomes superconducting below a certain temperature, and change the isotope whenever it is possible, because many elements have different isotopes, which are different by the number of neutrons in a nucleus, then it was seen that the temperature depends on the isotope mass, such a way it's inversely proportional to square root of mass. So you change the isotope, the temperature of superconducting transition changes. This is so-called isotope effect, which actually brought some conclusion that maybe the mechanism of superconductivity is somehow related to phonons. Because inverse square root of mass, this is precisely what you have when you consider your body on a spring with a stiffness, with a mass, then the frequency of your oscillations is inversely proportional to the mass, and then when you build up the theory of phonons in the crystals, you also saw that the frequency of the phonon modes are inversely proportional to the square root of the mass. So this was kind of argument, and therefore let's look at the Hamiltonian describing electron-phonon interaction. Did you discuss it in your lectures of solid-state physics or with Professor Narcisian? So how the Hamiltonian, simple Hamiltonian describing electron-phonon interaction looks like? Okay, so I will recapitulate, but I strongly recommend you to read the textbook for more details. I will give you a sketch of the derivation of this very simple Hamiltonian, and you will read more as your homework, so to say. So, we have Coulomb potential. So Coulomb potential between electrons is in the core of everything. So let's consider correction to energy associated with electron-electron interaction. This is something what we discussed a little bit when we discussed dielectric properties of metals. So this then will be proportional to the integral over dr prime, and you have density of electrons m at the point r. You have potential r minus r prime, and you have a polarization in the point of r prime. You discuss it in solid-state physics class. You move atoms, so phonons associated with vibration of atoms and displacement of atoms in a crystalline lattice. So by displacing atoms, you make a polarization, and there is certain correction to the energy based on that. Alternatively, you may think about time-binding model and expand hopping, take into account gradient with respect to coordinator, you'll get the same. I think you did this exercise with Professor Mercisan, how to get electron-phonon interaction in time-binding model. So, what is K? K r minus r prime, since electrons. This is electron-electron interaction, which is Coulomb interaction, which, as we know, in metals, Coulomb interaction is screened. So this is E square over r minus r prime if r minus r prime is smaller than the screening radius, Debye radius. So discussing the electric properties, we discussed also that there is no screening on very short distances. And for large distances, we have Yukawa potential. This is E square over r minus r prime times exponent minus r prime divided by rd. This is for r minus r prime larger than rd. So we got it from the dielectric properties of the metals. So the fluctuations of charge density lead to screening of the Coulomb potential. It becomes short range. So for our purposes, and I also mentioned that in real metals, the radius of screening is in principle of the order of the lattice constant. The charge is screened very efficiently in typical metals. In bad metals, the screening radius can be larger. However, let's assume we are talking about good metals, which means that without losing generality, I can replace K r minus r prime by the delta function of r minus r prime. This is very short range interaction, because at long range it's efficiently screened. So in a correctly extreme way, I can say that the interaction is delta function, which is a good approximation in the metals. Then I may say that this polarization is indeed related to the displacement vector, and we know how to quantize the displacement vector. You did it for harmonic oscillator, and this is indeed something related to harmonic motion of the atoms. So this is sort of B plus B dagger. This is a way to quantize the field of displacement without losing any generality, since it's only the delta function r minus r prime, and nr is the density. This is psi r modulus square. We can write down that this is some field phi r, which is associated with displacement. This is a real field. Therefore, the logic is like that. This is a correction to the energy. This correction to the energy is associated with certain expectation value of certain Hamiltonian. So now I'm saying that the Hamiltonian, whose expectation value will produce the correction to the energy, can be written down as some coupling constant G times integral over dr psi dagger r psi r times phi r. So, because this is already there, this is a delta function, and this divergence of the polarization is related to displacement, and this is some scalar field. Scalar because this displacement is scalar and displacement is real. It is given by the sum of creation and annihilation operator, which means it is real. So this is displacement field, and this is electron density. So this is electron-phonon interaction Hamiltonian. Written in terms of the first quantization. This Hamiltonian will produce this correction to the electron energy, to the energy of many-body system. Okay, let's write down the second quantized version of this Hamiltonian. Because now I would like to write it down in terms of A operators, creation and annihilation operators. I will second quantize these fields and this field. This would be B plus B dagger, and this would be A dagger and A. So the same Hamiltonian of electron-phonon interaction can be written down as sum over K, Q, and sigma. So I have some amplitudes, A, Q. Then you have A, K1 minus Q sigma, dagger, K sigma. This is how I Fourier transform electron density, and I have BQ by Q dagger plus B minus Q. Okay? So, to have some picture in mind, what then happens? You annihilated electron with a momentum K and spin projection sigma. You created electron with momentum K minus Q and projection sigma. Projection remains the same because no lattice vibration can lead to spin flip. This is just matter of motion of your atoms in the crystalline lines. Has nothing to do with spin. And then you can either emit phonon with a vector Q. So this is emission process. So you create creation operator phonon with wave vector Q, emission. However, you have complementary process, which is K sigma, K minus Q sigma, and you absorb phonon with a wave vector minus Q. So you have emission and absorption. And the fact that we have two processes, emission and absorption, is related to the fact that displacement field, this is a coordinate, this is a real field. Due to the same reason, for example, we have a property that I minus Q is equal to AQ star. You discussed with Professor Nersessian the scalar field, lambda to the phi theory, and when you discussed fluctuations, you probably, or Einstein-Cernicki theory, you had the very same property. I will use it. I hope you understand what I'm talking about. So, now, what I'm saying, that electron interacts with a lattice vibration such a way that he can transfer momentum and energy to the phonon by either emission or absorption. But let's imagine that one electron K sigma, K minus Q sigma, emitted phonon, and there is some other electron which is around with a momentum K1 and spin projection sigma, which can absorb this phonon. So this would be K1 plus Q and sigma. So this electron emitted phonon and another one absorbed phonon. what do we have at the end of the day? We have that electrons interact between themselves through emission and absorption phonons. Phonons are so-called mediators for electron-electron interaction. So at the end of the day, when we look at these processes, what happens then, electron with momentum k interacts with another electron with momentum k1, the energy and momentum is conserved in term, within this interaction, and this is electron and electron interaction mediated by the phonons. Okay, so let me call this process as a process A. It's associated with the fact that electron emitted phonon. However, I also have a process K sigma K1 K minus Q sigma when the electron absorbed, which means that yet another electron K1 sigma emitted this phonon K1 plus Q sigma. So this is minus Q. So these are two processes. And let me now, in a very simple way, derive the electron-electron interaction using the second order perturbation theory associated with emission and absorption of the phonon. So there are two terms in this interaction. Okay? Again, if you have a problem with logical steps, or if you have a problem with derivation, please ask question immediately. Because in many cases I do some sort of hand waving and simplistic derivation, but of course one may do much more rigorously derivation, but then for every derivation it will take one lecture, and I still hope to be able to do several things. So what means perturbation theory? I have interaction between initial and final state, and then I need to sum over all intermediate state Vs, V final S, Vsi, and then energy of initial state minus energy of the intermediate state. So for the process A, initial state is electron with a K sigma, and intermediate states, I will need to, sorry, am I correct? Yeah. And the final state, the final state would be the electron with a K minus Q sigma and phonons with a Q. So in this case, I would probably say that there is no summation. So this is just initial minus. So intermediate state, there was only one state. In this summation, let me remove it. This. And this is F, which is the same as S. So therefore, for the process A, what I have for this term, it's second order process. So in this term, I have amplitude AQ. For this vertex, I have amplitude A minus Q. So I have AQ modulus square. So in the initial state, I have energy epsilon K. In the final state, I have energy epsilon K minus Q plus H omega Q. Okay? So this is energy of electron in the state K, and what I have here is electron with energy K minus Q and phonon with energy omega Q. For the process beam,
excuse me. So from this diagram, why are we only considering one vertex? Actually, we have considered both vertex because we have taken AQ and A minus Q, but shouldn't the initial state should be like EK plus EK1? Considering
as I said, I have a conservation law, and conservation law, which I'm going to use just in the derivation B, tells me that epsilon K plus epsilon K1 is equal to epsilon K minus Q plus epsilon K1 plus Q. So this is energy conservation law. In principle, what I'm saying, in fact, I need to, well, let me restore. These are all intermediate state because at the end of the day, I will need to sum up all possible Q's. I am writing the diagram for one particular Q, but in principle, yeah. What I'm saying is, I'm looking at, I'm not going to compute two-particle green function. So in a sense, you would like to say, you want to say that this is initial state and this is final state. However, I need to integrate out all phonons. So therefore, I will take summation of all phonon processes. Therefore, I'm assuming that this is initial state, and in the one vortex I have this, but also this is second order process. I have to take the matrix element square. I don't know if it's sufficient for you or not. So, in the same way, I'm saying that process number B, this is precisely what you say. I will say that initial state is K1, then the intermediate state is epsilon K1 plus Q plus H omega Q, because at this vertex we have emission of phonons, and this is omega minus Q to be more pedantic, and this is AQ square. But since omega depends only on modulus of the wave vector, I can put plus here, and using the conservation law, I write that epsilon K1 minus epsilon K1 plus Q is equal to minus epsilon K minus epsilon K minus Q. Therefore, process B is AQ modulus square minus epsilon K minus epsilon K minus Q plus H omega Q. Okay? You understand? Therefore, if I combine processes A and processes B, is equal to A modulus Q square. I take it out of the bracket. The first process is emission process. The second process is absorption process. Epsilon K minus epsilon K minus Q minus H omega minus 1 over epsilon K minus epsilon K minus Q plus H omega. So this is then A modulus Q square times 2 times H omega Q divided by epsilon K minus epsilon K minus Q square minus H omega Q square. See, it's much better to do it with the help of green function than you just plug in the green function of phonon, which is this one, by the way, and you don't do this hand waving argument with the second order perturbation theory, which I agree with you are a bit confusing, but this is what we have. So this effective interaction between electrons is given by this expression, and this effective electron-electron interaction is mediated by phonon. Okay? This is, of course, retarded process. So one particle emits, sometimes after another particle absorbs it. But let's look at the expression which I have written down. Again, I prefer that you have a physical picture in mind. Suppose we have a Fermi surface. For simplicity, I consider spherical Fermi surface. Three-dimensional metal, whatever. And you take two electrons above the Fermi surface. Okay? So if we assume that energy of electrons with a wave vector k minus energy of electron with a wave vector minus q is much smaller compared to the energy of phonon, what we have here, we can neglect this term under this condition, which means that effective electron-electron interaction is equal to minus modulus A Q 2 divided by H omega Q. I neglect this term, I have sign minus, omega cancelled in numerator. So the conclusion which I draw is that two electrons taken very close to the Fermi surface, which exchange the phonon, namely one emits, another one absorbs, attract each other. So there is attraction mediated by electron-phonon interaction, and this attraction can lead to formation of the Cooper pairs. So now I'm coming back to the beginning of my lecture. I was saying that something with effective charge E and effective mass M star, E star superconduct the current. I forgot to say that although this was a logic of phenomenological theory, it appeared with very high accuracy that effective charge is equal to twice charge of an electron, and effective mass is equal to twice mass of the electron. Therefore, one can think that some pairs of electrons conduct this current. Again, in the original works of Landau, it was effective charge, effective mass, and they said that somehow this E star is equal to E and M star is equal to 2M, and it might be coincidence. Now I'm trying to advocate that this is not a coincidence, and I'm trying to build a block saying that two electrons attract each other. So in principle, they can form pair. And what I do in remaining 20 minutes would be solving the problem of two electrons above Fermi surface, which will lead me to conclusion that there is a bound state of two electrons. And this is Cooper pair, and then we may say that these Cooper pairs, like bosons, they superfluid and then conduct. I should say from very beginning as disclaimer, the spirit of what I'm saying is not fully correct. So although the calculations which I will give and provide, show to you are mathematically correct, the incorrect thing is that I don't consider the Fermi C, and I don't consider the size of Cooper pair. So in the reality what happens, the bound state which I will find is artifact of the simplifications of the calculations. But in reality what happens that your ground state of the Fermi liquid at temperatures below certain critical temperature appears to be unstable with respect to spontaneous formation of the ground state. This is not a bound state because, as we see on Friday, we estimate the size of a Cooper pair, and it appears to be much larger than the typical distance between electrons. Therefore, these Cooper pairs, which I'm going to show you, will largely overlap, and it is not legitimate to speak about Cooper pairs as isolated particles. So please close your eyes for the moment, and I will recommend it again on Friday. But at this, from now on until end of the lecture, I will assume that there are 2 electrons in the vicinity of the Fermi surface. I will forget about existence of any other many-body states which should be taken into account, and show that there is instability. You wanted to ask a question?
What makes them attract despite having the same charge?
Yeah, it's a good question. So your lattice vibration makes a kind of well, which lead these 2 particles effectively to attract, provided that they are very close to the Fermi surface. Of course, your question is absolutely legitimate. Nobody forgot that there is a Coulomb interaction, and the overall attraction of electrons should be seen as a competition between this effective repulsion associated with exchange of phonon, effective attraction associated with exchange of phonon, and repulsion due to Coulomb interaction. This is actually one of the ways to explain why not all metals are superconducting. Because in some metal, the total effective interaction is repulsive. But in some other metals, the effective interaction is attractive. So it's a matter of the material, I would say. On the last lecture of superconductivity, we will discuss a condition for that. There are renormalization of this electron-phonon interaction associated with existence of Coulomb interaction. This is actually a very interesting topic, but let's assume that Coulomb interaction, which is screened and very short-range interaction, is negligible for this energy condition, and this is the only condition what we need. Well, in principle, you are right, Coulomb interaction is almost there. In some cases, in many cases, it leads to appreciable renormalization, but there are some cases where the Coulomb interaction is indeed negligible, and there is a criterion for that when Coulomb doesn't play any important role and when it does. Okay, so, and what I'm going to solve now is very much related to one of the problems in your homework, when I just want you to solve the quantum mechanical problem, Schrödinger equation for the particle being in cylindrical well. Okay, so Cooper pairing. So Cooper, Leon Cooper is a physicist, so Cooper is a name. And Cooper pairing actually leads in the core of theory of Barden-Cooper-Schrieffer interaction, theory of superconductivity, which will actually rely upon the fact that the interaction between 2 electrons in the vicinity of Fermi surface is attractive, and it will, as we will see, the Monday lecture will show you how to solve problem correctly, how to solve many-body problem correctly, and just as indication that something goes on, I will solve to you 2-body problem, but not put very big emphasis, because the real problem which we need to solve at the end of the day is many-body problem. But 2-body problem is also instructive. So 2 electrons, the wave function which we are going to write down, we are going to write and solve some Schrödinger equation for 2 electrons. And as you know that both in classical mechanics and quantum mechanics, the 2-body problem can be mapped to a 1-body problem of the motion of some particle with effective mass. in the system associated with the centrum of mass of the particles. So I'm going now to write down my wave function in terms of proper coordinate associated with the motion of the centrum of mass and relative motion, and solve quantum mechanical Schrödinger equation with very simple potential, which assumes that there is a kind of nutshell of the width of Debye frequency. Suppose we have phonons, so the electrons attract each other in the skin of around Fermi surface of the thickness of twice Debye frequency, and you know Debye frequency is inversely proportional to the mass, to the square root of the mass of atom, and what we obtain will be kind of explanation for the isotopic effect, and the interaction is zero everywhere else. So I disregard Coulomb interaction. So as I said, we have two coordinates, R1 and R2, and we have two momentums, K1 and K2, to characterize this system of two electrons. So I will introduce the coordinate of the centrum of mass. This is R1 plus R2 over 2, and coordinate of relative motion, rho, which is R1 minus R2. So the electrons are almost free, so the basis of plane wave is a good basis. So basically I will be working with the plane wave, I K1 R1 plus times I K2 R2. So these are plane waves describing electron 1 and electron 2, but of course the true wave function can be expanded, can be presented in complete basis of plane waves, which I will use for construction of the wave function. So again, this is the coordinate of centrum of mass, and this is a coordinate of relative motion. The very same way I introduce K, which is this way. So K1 is equal to K plus Q over 2. K2 is equal to K minus Q over 2. Therefore, K is equal to, am I saying correct things? No. K1 is Q plus K over 2. It's minus Q plus K over 2. Therefore, K is K1 plus K2, and Q is K1 minus K2. So what I'm doing, I have K1 R1 plus K2 R2. I would like to represent it as I to the power chi K R times I to the power Q rho. You may check with what I did that this is correct. I can re-express R1 and R2 in terms of R and rho, and what I will obtain is K and Q. Which means that my wave function of the Cooper pair psi, which depends on R and rho, as I said, the two-body problem should then be considered in terms of the centrum of mass in relative motion. Without any losing generality, I'm saying that this is sum over Q and K. This is C Q, which depends on K, I K R plus I Q. I use complete orthogonal basis of the plane waves to write my wave function in terms of it. Which doesn't mean I solve problem. I just constructed correct basis. And now I'm writing the Schrödinger equation in the potential. So the problem is defined as follows. I'm going to solve single particle Schrödinger equation. Psi is equal to E psi. So the Hamiltonian consists of kinetic energy, and in the new coordinates of centrum of mass and relative motion, this is minus nabla over 2m capital minus, so this is nabla r, minus nabla rho divided by 2 mu plus v, which depends on rho. So the reason to come to the coordinates of the centrum of mass and relative motion is that interaction between particles, the interaction between two electrons, depend only on the relative coordinates. So here m is a total mass. This is m1 plus m2, which is twice mass of electron, and mu is so-called relative mass. 1 over mu is 1 over m1 plus 1 over m2, which means mu is equal to m1 m2 divided by m1 plus m2. So this is mass over 2 when we do have two identical vectors. So the total mass is twice of mass. The reduced mass is half of the mass. So this is how the transformation of coordinate system is done. So now I will write down my stationary Schrödinger equation in Q space using this form of the wave function. Before doing that, I assume that my potential, okay, let's write the Schrödinger equation. So k square over 4m plus q square over m. So this is this term times cq plus sum over q1 v q1 c q1 is equal to E times C. So v q q1 is the integral over v rho d rho e to the power minus I q rho I q1 rho. So this is a matrix element of the interaction. And I will assume that v q q1 is equal to minus modulus v naught if epsilon q minus epsilon q1 is smaller than h omega d by and 0 otherwise. Okay? So this is precisely the cylindrical well, because everything preserves a cylindrical symmetry. Since I have like 5 minutes and it will be enough, the first thing which I will do, I will assume that I am in the system of the centrum of mass. I will say that k is equal to 0. K, it's not necessary, this assumption. This says that two particles with k1 and k2 are in such state that the total momentum is 0. However, I may also consider the situation So the particles are on the diameter of the Fermi surface. I can also consider the situation when there is a finite momentum, and I suggest you to do this exercise yourself, and it's very instructive because you will find out that, like Landau criterion, there is a critical k or critical velocity. So your Cooper pair moves with some critical velocity, and something, namely the bound state, will be destroyed. Good. And okay, this is for simplicity of blackboard discussion. I write down that CQ is equal to minus, I will put everything in the right hand side. So this is Q squared over M minus P times sum over Q1 VQ1 CQ1. And what I do, I will take summation over Q on the right hand side and left hand side. And I assume that the interaction satisfies this criterion. So first of all, it doesn't depend on Q under this condition, and what I have in right hand side and left hand side is the same summation over Q1. So what I have then is 1, the interaction is attractive, is equal to plus modulus V node sum over Q 1 over Q squared over 2M, over M minus P. So this situation, since K1 is equal to minus K2, this is a condition to have centrum of mass momentum, means that Q, which is K1 minus K2 over 2, is equal to K1. And K1 is, of course, modulus K1, is approximately Fermi moment. Which means that Q is also approximately Fermi momentum. I can write Q being approximately Fermi momentum, but a little bit larger, as Q is Kf plus delta Q. Okay? If I have finite K, finite centrum of mass motion vector, I need to be more careful with conditions, and I need to consider this geometric constraints. But what I'm saying is that Q squared over M is equal to Kf squared over M plus 2 Kf delta Q over M plus O over delta Q. So, of course, I assume that the delta Q is much smaller than Kf. So I ignore this term. The condition that this state is inside the nutshell in the vicinity of Fermi surface reads that this energy should be between Fermi energy. So let's say Q squared over 2M should be Fermi energy minus H omega d. So this is the bifrequency, and smaller than Fermi energy plus H omega t. So then, what then I have is that Kf delta Q over M is between minus h omega d and h omega d. So now I will compute the integral in the right hand side, and I will find the binding energy. So we have 1 in the left hand side is equal to modulus V naught, because I have attraction, and this is very important. And here I have integral over dq over 2 pi square, or 2 pi cube, sorry. I have 1 over 2 Fermi energy minus E plus 2 kF delta Q over M. And I will denote this as new variable. So 2 Fermi energy minus E is denoted as epsilon. So if I will find that this epsilon, which is the eigenenergy, related to eigenenergy, is positive, which means that the epsilon is smaller than twice Fermi energy, which means that I have bound state. So if and only if I find a solution with a positive epsilon, I will conclude that 2 electrons subject to attraction form a bound state. So I will continue it this way. 1 is equal to V naught, and here I have 1 over 8 pi cube. The integral over dq. As I said, I come to the spherical coordinate system, so I write it down as 4 pi q square dq. But now I assume the q is almost kf, and only delta q changes. So this is 4 pi kf square times d delta q. Therefore, it is 4 pi kf square integral, and now I need to integrate over d delta q. Here I have epsilon plus 2kf delta q over m, and this is condition for delta q. So delta q changes from minus, I put h bar equal to 1, minus m omega d divided by kf, to plus m omega d over 2kf. So let's introduce dimensionless variable 2kf delta q over m equal to x. So therefore I have 1 in the left hand side is equal to modulus V naught times 4 pi kf square divided by 8 pi cube. This is what in the left hand side. Then I multiply and divide by m over 2kf. Therefore, I have integral over dx, and here I have epsilon plus x. So the only thing is the limit of integration, which is now from minus 2 omega d to, plus minus 2 omega d. So I should multiply here. Oh, there is actually no. There is missing, the lower limit was written correctly, the upper limit is m omega d over kf. I multiply by 2kf over omega m, and this is what I obtained. Okay? So I cancel out this m, I cancel out 4 pi and this 8, this is 2 pi square. And I have now this integral, which of course I will replace by the integral from 0 to 2d. So what I'm saying is 1 is equal to modulus v naught times mkf over 2 pi square times 1/2 times times 1/2, yes, times 2 integral from 0 to 2 omega d dx epsilon plus x. Yeah. Good. So this is 1/2 of the density of states at the Fermi energy. If you remember this, and the integral is of course logarithm, as we anticipated before. So this one is logarithm over 2 omega d plus e over e, and we have 1/2 v naught times density of states at the Fermi energy.
Excuse me, sir. Is that it doesn't seem like an even function. So
Yeah, that's of course correct. So in this sense, I will put epsilon. We will see actually that the logarithm, epsilon is exponentially small. This is what we see. Of course, I can present this as something plus correction. And as a homework, you may estimate this correction. This correction is nicely converging, but you're right that the integral is of course not the integral of the even function. However, the main value, the main logarithmic contribution which I am about, is obtained inside this approximation. The correction due to not fully even form of the wave function is not logarithmical, so I disregard it. Good. I obtained the equation for epsilon because I'm about to solve Schrödinger equation and found the eigenenergy. And let's for the moment assume it will be confirmed by the result that this epsilon is much smaller compared to frequency. So I will call this as G, and therefore by solving this equation I obtain that epsilon is equal to 2 omega d by e to the power minus 1 over G. So I obtained that epsilon is 2EF minus E. It is positive, which means the eigenenergy E is smaller than twice of energy, Fermi energy. So attraction between two electrons in the vicinity of the Fermi surface results in reduction of the eigenenergy compared to the energy of free particles. So these two electrons form bound state, and the energy of this bound state counted from the Fermi energy is exponentially small with respect to coupling constant. 1 over coupling constant. So what I obtained, that two electrons form the bound state with exponentially small energy. And this bound state is called Cooper pairing. What we will see when consider the Bcs theory, that when we consider true many-body state, namely many electron state in the vicinity of Fermi surface, we will see that the ground state of such a system subject to attraction is unstable. So the Fermi liquid cannot exist as a ground state due to attraction between electrons, and the new ground state which we obtain is characterized by the gap in the spectrum of excitations, and we will see that the meaning of this equation is the behavior of the gap. So the exponentially small gap exponentially with respect to inverse coupling constant, which means one cannot get this result by using perturbation theory. It's non-analytic. The pre-exponent is the Debye frequency, is the true ground state of the problem. Moreover, the critical temperature of the transition to new ground state will be also given by such formula with a little bit different coefficient of the order of 1. So we then explain that the critical temperature is proportional to Debye frequency, this characteristic frequency of phonons, which is itself inversely proportional to the square root of the mass of the atom, which then explains the isotope effect. So even this simple calculation, namely existence of the bound state, tells you that something happens with the electron system. Well, 2 electrons is too simple, too naive, but 2 electrons lead us to some conclusion, and the true solution actually supports this conclusion. Yeah.
Do these 2 electrons experience the same field? Okay, I'm asking it because it's like, why do we have to give them different masses if they're like in the same system?
No, there is nothing about, well, I said that the masses are equal. So when I wrote equation, this means that the reduced mass, I consider 2 identical electrons. I said that total mass, which is m1 plus m2, this is just a twice mass, and the reduced mass mu, which is 1 over m1 plus 1 over m2, this is 2 over m. So the reduced mass mu, this is 2 mu, and therefore, since mu is m over 2, I wrote m. So no problem with that.
Okay. Then, which field is screened by the semiconductor? Is it this field due to a passage of current in a conductor?
What is semiconductor? Okay.
Again, there is this diagram we drew and talked about the magnetic behavior.
There is no magnetic field. I consider problem without magnetic field. It has nothing to do with the first part of the lecture. As I said, to explain Meissner, I introduce a response of a superconductor to the magnetic field. Here, I just consider the mechanism of formation of the bound state of just 2 electrons taken separately or taken in the vicinity of Fermi surface. And indeed, I tell you that if I ignore all other electrons which appear in the vicinity of Fermi surface and consider just one body problem, where the one body is related to this 2 body in the system of the center of mass. This one body problem is then unstable with respect to formation of the bound state. Nothing about magnetic field in this story at all. Why do you mention magnetic field? I stopped talking about magnetic field when I start discussing electron phonon mechanism.
I talked about it because of these 2 diagrams. In one, the field is not passive.
Yeah, it was beginning of lecture. I explained why magnetic field doesn't penetrate and stop considering magnetic field.
Just needed the clarification why you talked about their magnetic behavior between the lines.
I talked about magnetic field behavior in order to justify the hypothesis that there is a superfluidity of something. So in order to explain why there is no magnetic field inside superconductor, I need to justify that the superconductor can be described by the global wave function, and there is superfluidity of something which then explains the superconductivity. But this superfluidity of charged particles results in repellent magnetic field outside of the superconductor. So my first part of lecture devoted to phenomenology was actually motivated and argumented to justify for you that superfluidity and superconductivity are closely related topics. What we do Friday, we will keep doing these superfluid derivations, but for the order parameter which depends on the coordinate. So we derive these Ginzburg-Landau equations, and we will see that one can do a little bit more, not little bit, much better analysis, and actually derive all this Meissner effect and equations describing superconductor from the approach known in the phase transition theory. This is what I'm going to present next time. But the second part of the lecture, when I consider electron-phonon interaction, attraction due to electron-phonon interaction, and bound state, was completely unrelated to magnetic field behavior. As I told you from the very beginning, I start to build ingredients and arguments for the microscopic theory. Because I wanted to explain where this E star comes from and where this M star comes from. And now, with all these calculations, I'm argumenting that E star is probably related to the formation of a Cooper pair, and therefore E star is equal to twice charge of electron, and M star is equal to twice mass of electron. Therefore, what superconducts are Cooper pairs, which is in full correspondence with experimental observation. I agree that today, Friday, and Monday would be probably the most difficult lectures of the course. But these lectures are in the middle, and you need to work hard in order to digest it and in order to understand it. More questions?